This is a spotlight video for our paper, Inhomogeneous Hypergraph Clustering with Applications. Graph clustering is a process of grouping vertices in a graph according to some predefined constraints, most often requiring that one maximizes the number of edges within the groups and minimizes the number of edges across groups. In graphs, edges capture pairwise relations, but in practice, relationships between objects may be more accurately captured by higher-order relations, which are not necessarily observed at the pairwise level. In this context, it is necessary to use hypergraph models where hyperedges describe these high-order relations. This introduces the problem of hypergraph clustering, where each hyperedge is associated with a scalar weight that indicates the strength of the connection between vertices within that hyperedge. However, different vertices may have different structural importance within a hyperedge. Hence, one needs to describe the weights as vectors that contain information about the importance of different vertex subsets. This leads to the new notion of an inhomogeneous hypergraph. Specifically, in an inhomogeneous hypergraph, each hyperedge H is endowed with a weight WH, that is a set function, where for a given subset S of H, WHS denotes the cost of splitting H into S and its complement. The goal of inhomogeneous hypergraph clustering is to minimize a properly defined normalized cut function. We propose an efficient three-step algorithm to solve the inhomogeneous hypergraph clustering problem. The first step is to project each hyperedge into the subgraph and approximate the inhomogeneous weights. The second step is to merge the obtained subgraphs into a new graph. The third step is to perform a standard spectral clustering algorithm on the obtained graph. The algorithm has provable theoretical guarantees under some mild conditions. Constant approximation results can be guaranteed whenever the inhomogeneous weights are submodular. To this end, we derive an explicit formula for the optimal linear projection. This linear projection gives the best known constant approximation results when the size of hyperedges is moderate. We identified many new applications for inhomogeneous hypergraph clustering, including hierarchical network motif clustering tested on the Florida Bay food web, structural learning of ranking data tested on the Irish Parliament election data, and subspace clustering tested on the Hopkins 155 data for motion segmentation. In all cases, all methods improve the performance of the methods based on homogeneous hypergraph clustering, as well as other methods tailor-made for solving the particular problem. Thanks for your interest, and please check our paper in NIPS 2017.